Okay, continuing on, logarithms, right? We had an example 13 that Jane had $400 to invest. She needed to know when it grow to 600 years at 6% annual interest, compounded continuously. By using the intermediate value theorem, we found that it's about 6.75 years. But how can we find the exact time? So basically the idea is that if you have an exponent, you want to be able to find out, if you have an exponential equation, you want to be able to find out what the exponent is. And so if you think about what the graph of an exponential function looks like, we'll just do a little sketch here, right? That passes the horizontal line test. And we know from section 1.8 that that means if you pass the horizontal line test, that means you've got an inverse function. So exponential functions take you from x to y. The inverse function takes you from y's back to x, right? And the inverse function to an exponential function is called a logarithm. So the inverse to y equals b to the x is y equals log base b quantity to the x. This is just the name of the function. The b, it's a logarithm. The b is the base. And the x here, that's the variable. Okay? And so the subscript b there, that's just telling you what the base is. It's just a little information about which base you're using. X is the variable. So you can graph logarithms. What's the graph of a logarithm look like? Well, remember that the graph of an inverse function, right? So we know the graph of y equals, what is this? Y equals 2 to the x. Looks like this. How do you get the graph of the inverse function? Well, you take the line y equals x, and you take this graph, you flip it over that line, and that gives you the graph of the inverse function. So 0, 1, that's on the graph of y equals 2 to the x. So the inverse means just flip those numbers, right? Flip the y to the x and the x to the y. So this 1, 0, that's here. And so that's going to be on log base 2 on the inverse, graph of the inverse function. So this point is 1 equals 2 to the 0. Right? Plug in x equals 0, you get out y equals 1. This point is 0, is my y value, equals log base 2 of 1. That's my x value. So the 0.01 and the 0.10, you can rewrite them as exponential logarithmic forms. For 2, this is on the graph of y equals log base 2 of x, because 4 is here, 2 is there. So that's the point 4, 2. What's the corresponding point on the graph of the exponential function? You flip it over this line, and you get, right, the point 2, 4. So the inverse is 2, 4. This is on the graph of y equals 2 to the x. So 2, my y value, equals log base 2 of 4, or 4, that y value, is 2 squared. So we have two numbers, 2 and 4, and we can represent the relationship between them in terms of logarithms or in terms of exponentials. So as an inverse function, right, they have a graph. It looks like this. This is sort of a standard graph. Note that, again, my x-axis, 2, 4, 6, 8, 10, 12, 14, 16, 18. My y-axis, 10, 5, minus 5, so this is stretched out a little bit. But here's the graph of log base b of x. The domain is x is greater than 0. We just start here and go out to the right. If you take this graph, which has a horizontal asymptote here, and you flip it over this line, you miss the entire left side of the graph. So there's no, logarithms have no graph out here to the left. Right? The domain starts at 0 and goes out to the right. It doesn't include 0. Range all y, or minus infinity to infinity. Remember that when you're looking at inverse functions, you flip the y and the x. So the domain of the logarithm is the range of the exponential function. So this domain is 0 to infinity. That's the range of exponential. The range of the logarithm is the domain of the exponential function. So that's all numbers. What are the special points? X equals 1. X equals 1, y equals 0. That's one special point. And on this graph, because it's y equals log base 2 of x, I'm having a base of 2. When x equals 2, y equals 1. But in general, if your base is b, then you get 1, y equals 1. Your vertical asymptote, the graph goes all the way down, gets very, very close. It's very, very close to the y-axis, but doesn't actually touch it. That's called the vertical asymptote, and that's at x equals 0. So basic features of a log graph. And of course, they can be moved around just like anything else. Graph this thing, right 2 units, up 5. What's the basic graph? Log base 3 of x. The basic log graph looks like that. This is the graph of y equals log base 3 of x. And then we moved it by moving it right 2 units and then up 5. So what are the basic points here? X equals 1, y equals 0. X equals 3, y equals 1. And a vertical asymptote at x equals 0. So the point 3, 1 goes right 2 units and up 5. So it ends up at 5, 6. The point 1, 0 goes right 2 units, so you get to 3, 0, and then it goes up 5, so you get to 3, 5. And my vertical asymptote is x equals 0, moving it right, moves it to x equals 2, moving a vertical line up. If I take a vertical line to move it up, it's still the same vertical line. So moving it up doesn't affect the vertical asymptote, but moving it left and right does. So what does my graph look like? 1, 2 is where my vertical asymptote would be at 3, 1, 2, 3, 4, 5. We'll go through 3, 5, and then at 5, so 4, 5, it goes through 6. I'm supposed to curve a little bit there, but there's our graph. It's more or less like that. So it's a graph. It can be moved around. We have to be a little bit careful about domains, though. Logarithms have restricted domains. So here's the thing we did with domains a long time ago. In this class, you can't divide by 0. So if you have x divided by g of x, any solutions of g of x equals 0, those can't be in the domain. You can't have negative numbers in a square root or any even root, like a fourth root. So if we have square root of f of x, whatever's inside here, that better be positive. You can't have negative numbers or 0 inside a logarithm. So if you have logarithm of something, then you have to take whatever it is bigger than 0 and try and solve it. Any function that isn't one of these 3 cases, right? No division, no square roots, no logarithms, then the domain is all reals. So domain of this, right? This is the division by 0 case, x squared minus 4 equals 0. Any solutions to that are bad. You can factor x squared minus 4 to x minus 2, x plus 2. So what's the domain for this function? All x except x equals 2 or minus 2, because that makes the bottom 0. Here's a function with a square root. What's the domain there? Take what's inside the square root, make it, and say, well, that's got to be positive 3x minus 7. Then you can solve that. Take the 7, move it over the other side, divide by 3. You get x has to be bigger than or equal to 7/3, or there is the domain for that square root function, only numbers between 7/3 and infinity, because if you use numbers less than 7/3 and you plug them in there, you get a negative number inside the square root, and we really don't want to deal with that. C, take x minus 2, right? That's the thing inside the logarithm, make it bigger than 0, so x is greater than 2, that's your domain. This function is actually the function we graphed here, and you can see that this function, right? The domain, the graph is only over the part of the x-axis that's from 2 out to infinity, right? So the domain is just x greater than 2. If we have something more complicated, like log base 5 of x squared plus x minus 12, you need to know where that's greater than 0. How do you do that? Take this function and graph it. If you factor it, it becomes x plus 4 times x minus 3. We've got x-intercepts at minus 4 and at 3. It's a parabola, right, that opens up. So your graph looks like, here's minus 4, here's 3. Right? And what we're interested in is what parts of this graph are above the y-axis, above the x-axis, right? What y's are bigger than 0? So my domain for this function is minus infinity to minus 4. That's this part of the graph. And then that part of the graph corresponds to x bigger than 3. So if you have something a little bit more complicated than just like a nice linear function that's easy to solve, graph this thing, figure out where the graph is above the y-axis and the corresponding x's of the domains that you want. So the domain of this function is minus infinity to minus 4, union 3 to infinity. Okay.